Okay, our next talk is Ron Cohen talking about probabilistic termination and composability of cryptographic protocols.
Okay, thanks. I'll talk about how to compose secure computation and Byzantine agreement protocols. And it's a joint line of works with Sandro Coretti, Juan Garay, and Vasilis Zikas. Like prior talks, we talk about secure computation where we have a set of parties and we want to compute some task together. Say, compute a function jointly on our secret inputs. And normally the way we define security is by thinking of this idealized world, this dream scenario, where we have a trusted party that does the computation for us. And we say that the protocol is secure if no external identity, no environment can distinguish between the two worlds. So this environment gives input to the parties, and it cannot tell whether they run a protocol or whether they use this external trusted party to do the computation for them. In terms of security, we want to say that for every attack on the real protocol, we have a simulator that can simulate the same attack in the ideal world. And that's a very, very strong definition. It gives us correctness, privacy, but even more so, it gives us composition. So we can now design a protocol where we have a trusted party that is responsible for specific parts of the computation of the protocol. And if we have a sub-protocol that realizes those parts, we can replace the sub-protocol, the ideal functionality with this sub-protocol. And if we can now distinguish between them, then we have an attack on the protocol that cannot be simulated, roughly same. So that's a nice goal. And one of the basic primitives that have been considered in secure computation is broadcast. Just a party that can send the message reliably to all other parties. And in this talk, we'll talk about the relations between broadcast and secure computation, and it turns out that these are complicated relationships between the two. We'll start with the love. So MPC loves broadcast. If we have a broadcast channel available, then there are many things we can do, and essentially everything that can be computed can be also securely computed. And more concretely, I'll talk about honest majority and guaranteed output delivery. So with the broadcast channel, we can compute any function in this very strong setting. So no matter what the adversary is doing, it cannot disrupt the honest parties from obtaining the output from the computation. In terms of round complexity, how much it costs us to compute the functions, so we know how to compute the information theoretically without relying on cryptographic assumptions in order of the depth, the multiplicative depth of the circuit representing the function. So we have round complexity, which doesn't depend on how many parties actually run the protocol. If we assume one-way functions, we can already get constant round protocols, and under stronger assumptions, we can get even two-round protocols. And all of these results we get under very, very strong guarantees of even adaptive corruptions of the parties that participate. Actually, broadcast is very good for secure computation because all of the protocols that we saw in the previous slides, if they are secure under parallel composition, we can run them in parallel. So take these two-round protocols, we can run polynomially many instances of these protocols, and it's still going to take us 2 rounds. So that's even a better property that we have with those protocols. But that brings us to the hate. What happens if we don't have a broadcast channel? Now we have to actually implement broadcast, and that raises very, very subtle questions that arise. So classic results tell us that in the plain model, we have broadcast protocols if and only if at most 1/3 of the parties are corrupted. And if we want to get more than 1/3 corruptions, then we need some trusted setup, a public key infrastructure, for example. And interestingly, there are some interesting functions that can be computed even without setup and without broadcast, with guaranteed output delivery. But for the rest of the talk, we will assume that if we have more than 1/3 corruptions, we'll have this limited setup assumptions, only PKI or information theoretic PKI, if we want security against computationally unbounded adversaries. What do we know about the round complexity of broadcast protocols? So there's a very well-known law bound that says that any deterministic protocol that is resilient for T corruptions must run more than T rounds. There's a less known law bound that says that randomized protocols that are R rounds will fail with probability roughly 1/R to the R. Yes, Elaine? Which one? Here? Yeah, so there are functions that can be computed even in the honest majority setting with robustness, with guaranteed output delivery. There are also functions that can be computed with guaranteed output delivery if I see in any number of corruptions. Yep. Yeah, we have non-trivial functions. So for example, the Boolean OR function, where everybody has an input bit and we compute the OR of those bits, can be computed facing any number of corruptions and without any broadcast assumptions. Yep. So going back to round complexity, we know some lower bounds on the round complexity of broadcast protocols, but we also know some upper bounds. So starting from the seminal works of Benor and Rabin in the 80s, we know how to compute broadcast or Byzantine agreement in expected constant number of rounds, and we do get guaranteed delivery we are sure to terminate within polylog many rounds. But in expectation, we only need a constant number of rounds. And every time I give this talk, I need to add another protocol to this list, so it seems. Those first protocols, those expected constant round protocols, they have what's called probabilistic termination. So we know when we start the protocol, but we have no idea when we'll actually finish running the protocol. So we don't know ahead of time how many rounds we need to run. And even more so, if I finish the protocol, I have no idea if everybody else have finished or not. We don't have simultaneous termination. And those properties give us already a bit of a headache when it comes to composition. Because if we don't finish together, then under sequential composition, we cannot start the next instance together. And if we need to start together the protocol, that already gives one issue. But even more so, it turns out that if we run in parallel many instances of expected constant round protocols, the parallel composition will no longer be expected constant. And yeah?
Sequential composition, because most of these protocols have the property that if I terminate, I know everyone else will terminate in the next round.
Yeah,
so like you can just absorb the delta into the network delay.
Yeah, we'll get to it. That's a good point. But if I don't know, I know that I have some guarantee about how many rounds we can get, even one round, but I don't know when I need to start the next protocol. And we'll get to it in a few slides. That's a good point. About the parallel composition, then just to give an illustration, if we have a geometric distribution, then we know we have this logarithmic blow-up because the maximum of the expectation is not the expectation of the maximum. So think of coin tossing. If I toss a coin and I want to stop when it's heads, then in expectation I need 2 tosses until I fall on head. At most 2 coin tosses. But if I toss n coins in parallel, and I want each one to fall on heads, then after the first toss, roughly half will fall on heads, and if I need to throw again. After the second toss, another half of those will be heads, and another half won't. So I get a logarithmic blow-up in the round complexity. And those issues are nothing new. We know how to compose sequentially Byzantine agreement protocols, such that if we have m instances, then we'll only need expected m number of rounds, which is what we want. Also, we know how to compose polynomially many instances of Byzantine agreement in parallel and still have expected constant number of rounds. Again, that's what we want. So if we have what we want, what's missing? So all of those prior works prove in the property-based definition of Byzantine agreement. And remember the first slides, if you want to argue about composition, then the way that we basically know is this real ideal paradigm. We want to have a trusted party that is in charge of the broadcast, and then to have a protocol that simulates this trusted party. And then we can replace them. If you only have property-based definition, then it may be composable, but I have no idea how to argue about it. And it turns out that the main challenge is to simulate this probabilistic termination aspect of the protocols. So the setting that we look at is synchronous, secure channels. We have pairwise secure point-to-point channels with privacy, and we have a synchronous communication network. And concretely we use the framework of Katz, Maurer, Tuckman, and Zikas from TCC 13 that showed how to model synchronous communication in UC, but that's just for concreteness. The same results will hold in any natural synchronous model. In their model, they talked about exactly this real ideal paradigm for synchronous communication, and the idea is that the environment in a synchronous protocol can see after how many rounds the protocol terminates. So that's something that we also have to emulate in the ideal world. So every functionality is parameterized by how many rounds the protocol that implements it is going to run, and it will simply store the output until so many rounds have passed. And parties, instead of having the functionality give the input to the parties now ask the functionality for the output, so the functionality can this way count how many times it's been poked to fetch the output, and keep the round structure also in this ideal model. That's roughly what happens in the TCC 13 paper. But when we talk about this probabilistic termination, there are many subtle issues that arise. And just before going over the framework, I want to go over an abstraction of Feldman-Michaelis protocol of randomized Byzantine agreement to see where the issue comes from. So the protocol goes in epochs or phases. In each phase, the parties first, if they start with the same input bit, they will terminate in this phase. Otherwise, they run some sort of coin tossing, oblivious coin tossing, that will succeed with a certain probability and will fail with another, but the parties don't know whether it succeeded or not. If the coin toss succeeded, then they will terminate in this phase. But if the coin toss failed, then now the adversary gets to choose. Either the parties would run another phase, or it can make some parties terminate, while other parties will move on to the next phase. But in this case, we have a guarantee that they will finish in the following phase. So the adversary can basically split the parties into fast parties and slow parties, where the slow parties will finish one phase after the fast parties. So now we designed a framework to capture this probabilistic termination aspect in the UC framework. And the main underlying idea is to separate the function, what we want to compute in a functionality, from the round structure of the functionality. So the atomic building blocks are something we call canonical synchronous functionalities. And these are very, very simple functionalities. They have an input phase where everybody gives input to the functionality, and an output phase where everybody gets output from the functionality. And such a canonical functionality has two parameters. The function that it will actually compute, that gets one input from every party and one input from the adversary, and some leakage that the adversary will learn when parties give input. So party starts giving input to the functionality, the adversary gets the leakage that is supposed to, then the adversary gives his own input. That's the first phase, the input phase of the functionality. Next, parties ask to get the output and they get it immediately. That's the output phase. So it's a very, very simple functionality. One input round, one output round. And although it's simple, it can actually capture a lot. So if we have a secure function evaluation where we want to compute some function g, then basically we ignore the adversarial input and we compute the function g on the input of the honest parties. And the leakage just gives the length of the inputs to the adversary. Broadcast, we simply, everybody gives input and we take the ith input, the sender's input, and give it to everybody else. The leakage will only be, again, the length of the message. And it's very easy to get a parallel version when everybody gives input and the output of every party is a vector of the inputs. But if we want to model Byzantine agreement, which is not a function, we can also do it in that setting, because now we can see that if we have sufficiently many inputs which are the same value, this will be the output. Otherwise, we let the adversary choose what the output is going to be. And the leakage is actually the values that parties give, because we don't have any privacy aspects here. And modeling it like that allows us to actually simulate many of the Byzantine agreement protocols. So I think it's a natural way to look at Byzantine agreement as a functionality. Given those canonical functionality, those simple functionalities, we can now construct simple protocols. So it's, I heard that some people call such a model where at every point in time only one thing happens, a standalone composition. So it's protocols like in the 80s, like we know how to deal with. So the protocols will consist of such canonical functionalities, where in every round only one functionality is invoked. Parties give inputs, get output. So if you look at the Feldman-Micali protocol, it will look something like that. Parties send their input towards everybody else. Then they run those phases where they toss a coin and do a voting. Toss a coin, do a voting, until they get the output. And now we can actually, it's very easy to prove security. That's like security proofs that we used to in the standalone model. But we cannot, normally we won't be able to implement such a two-round functionality. So that's not enough. We need to somehow wrap it with a round extension wrapper. So we have, in the deterministic termination case, we simply add a wrapper that tells the functionality how many rounds it should run. And it would simply ignore the party's request to get the output until the last round. So it would sample the round in which it would finish. It gives it to the simulator to help him simulate the execution. Then parties give input like before, and the adversary gets the leakage. And then the honest parties start asking to get the output again and again and again until they get to this termination round. And we allow the adversary to give this input, not at the input round, but also slightly later. That's again helps us simulate many of the protocols. Once we get to the last round, the functionality gives the output to the parties. So again, that's nothing special. That's essentially the model of the Katz et al. For the probabilistic termination, now we sample some termination round, but this will only be an upper bound on how many rounds we actually need to run. And in addition, we allow the adversary to make some parties finish before others. So at the beginning, we tell the simulator what's the actual round that we sample, and then we give input. The adversary can instruct that some parties will get the output faster, and they will get the output, but other honest parties won't get the output at that point. It is guaranteed that when we get to this termination round, everybody will get the output. So now where do we stand? We can look at the Feldman-Micali type protocol, and it will actually realize a wrapped Byzantine agreement functionality. Again, assuming all parties start together. That brings us to the second part of the framework, how to deal with this non-synchronous, non-simultaneous start. And the main idea is once we have sequential composition, we have concurrent instances. We may start another instance before everybody finished. So we have concurrency here, concurrency issues, but we want to make this overlap meaningless. And if we start within C rounds from each other, we simply blow up the round complexity by 3C plus 1 rounds in the following way. So let's say the party on the left is fast, the party on the right is slow. At the beginning, nobody does anything, only listens. In the second round, in case C equals 1, in the second round, the fast party will send a message, and we know that the slow party will already start listening, so it will receive the message. In the third round, the slow party sends the message, the fast party still listens. And then, for technical reasons, in the framework, we had this dummy round where we don't do anything. And that concludes one instance of a message transmission for the fast party. Later on, the fast party starts another instance, but the slow party didn't finish the previous one first, but it gets into this round where it doesn't do anything, so we get this notion that the overlap is meaningless. It won't affect the security of the protocols, and the parties proceed this way. So we see that although we have concurrent composition, we actually get local sequential composition. And that if we look at round R, then we are guaranteed that when we send round R messages, all of the R-1 rounds messages have been arrived, and none of the R+1 round messages have been sent. So we do get synchrony in that sense. But if we are not careful, then we can get exponential blow up in the round complexity in that case. And as Elaine pointed out, using known techniques that go to Bracha in the 80s, we can make that the difference between the parties will only be one round. So we capture this behavior using another wrapper that deals with this non-simultaneous start issues. And to illustrate the composition theorem that we get, if we have a simple protocol that only has canonical functionalities, which realizes a wrapped functionality, then we can compile everything using these double wrappers, and we get that now even when we don't start together, we can implement this doubly wrapped functionality. And we can see from the slide how to do the composition. Because now if we want to have a sub-protocol for one of the functionalities, we simply have a simple protocol that realizes the single wrapped functionality. As applications, we get composable versions of parallel broadcast in expected constant round, and we plug it into the MPC protocol just as one would expect to get the same expected round guarantees as if we have a broadcast channel. So we don't have any dependency on number of parties. So that's good. Finish in 2 minutes. But still we have more issues, because now if we look at the MPC protocols that we get, they also have probabilistic termination on their own. So if we run them in parallel, we'll again get some blow up in the round complexity. And when we look at the solutions for parallel broadcast, they depend very heavily on this privacy-free aspect of the broadcast. And it's not clear how to generalize these techniques to the MPC. So I won't have time to go over it now, but we do have a way to compose in parallel also MPC protocols with privacy in a way that retains the round complexity or the expected round complexity. And we are black box in the protocols that we are compiling. But if we look at a stronger black box variant, then we show some impossibility results. But I need to wrap up. So just to conclude, we mostly discussed about how to model probabilistic termination, how to define protocols in a simple way and compile them into composable variants. We mentioned how to deal with composition of probabilistic termination protocols of MPC protocols with privacy. But actually, there are still open questions, and there is ongoing work now of extending this model also to partially synchronous and asynchronous protocols, or as Elaine mentioned earlier, the best possible partition tolerant model. And I think that can be a nice tool to look at blockchain protocols that rely on fast Byzantine agreement and to have a tool to argue about their security. So we have now a way, we are working on moving that to the permissionless setting, all of this functionality treatment. So, thanks.
I guess in this parallel part, I guess is the issue that you have to spawn multiple instances and they have to have consistent input. The part that you skipped, it sounded quite interesting.
So maybe we can talk about it offline.